Okay, welcome to this video for Chem 161, continuing on some content from Chapter 3, where we'll touch on some distribution functions that ultimately define our electron orbitals, and we'll look at the Aufbau principle, Hunds rule, and some energy level diagrams for the orbitals in an atom for where the electron could be located. And ultimately, we'll see some electron configurations for an atom. Okay, so I'll just put this as electron config for now. Great. Okay, so let's start. There's a lot on this slide, but I wanted to try to get some ideas through. We learned in a previous video that orbitals will be described by four principal quantum numbers. The first describes the rough energy level of an orbital. The second describes the shape of that orbital. The third speaks to the orientation of that orbital. And the fourth would touch on the spin state of an electron, and we saw there were two options there. So the first two principal quantum numbers are kind of giving us information in the top part of this slide. And the third quantum number is helping us distinguish between options that we see down here at the bottom of the slide. So let's start seeing if we can put some of the ideas we've had so far together. We saw earlier that quantum mechanics allowed us to calculate the probability of finding an electron, and in a Cartesian coordinate system where we had x, y, z directions for 3D space, the quantum mechanical calculations would tell us the likelihood of finding an electron, and we represented that with a pixel in that graph. So here's just sort of a version of that idea here. The graph below it represents what we call the probability of finding the electron as a function of the distance that we travel away from the nucleus. Okay, so I'll just sneak that in here. Distance from the nucleus. And the units for this are picometers. So we're very, very close to the nucleus at this point. And you can see here an orbital is drawn below, and our 0 point on this graph is lined up with the origin of that XYZ Cartesian coordinate system in our graph. So that is the cross point there, the crosshairs of X, Y, and Z line up with the 0. The graph is telling us that as we move away from the nucleus, that we quickly climb and build probability of finding the electron, and eventually this drops off and we have very little probability of finding it at long distances from that nucleus. And so we had the idea that 99% of the likelihood of finding the electron could ultimately give rise to this sort of size of this orbital. And that's the general consensus that we use to define the ultimate size of an orbital in question. Okay, so in this particular orbital that we have here in our first example, this is a 1s orbital. Recall that the 1 speaks to the first quantum numbers. That's our principal quantum number indicating n equals 1, and that's indicating the energy level. So this is the lowest energy level option. The s indicated that we had a certain L value. So that was an L value of the allowed 0. So when L equals 0, we have an s orbital, and s orbitals are have a certain shape, and they're spherical in nature. Okay, and so we know when we see s, we equate two things, L equals 0, and we see that we're dealing with a spherical orbital there. Okay, and the size of this spherical orbital is a function of the probability versus distance curve that we get from quantum mechanics. When we move up to the next energy level, so let's go to a principal quantum number value of 2, we move into the next set of information. Okay, so n equals 2, and we are still allowed to have an L value equal to 0. So we can have a 2s orbital, therefore. And so a 2s orbital, again, is going to be spherical, given the s label there, and the L equals 0 option. Now, we are higher in energy at this point, and so it might make sense that if we're going to reflect higher in energy, we're going to see electrons located further from the nucleus being more reactive, higher in energy. Okay, so again, we have a probability map shown here again, our same graph. Probability is the y-axis, and our x-axis is the distance from the nucleus. The 0 point in this graph lines up nicely with the center of this atom. And as we kind of walk away from the nucleus, we build probability, and ultimately that probability kind of climbs downward. And at some point, we cut off the graph and say 99% of our area of this graph is at this point, and that's going to help us define the size for this orbital. Now, something interesting arises when we have cases of s orbitals that have that are located in n values greater than 1, so 2, 3, 4, etc. We start to see nodes, so that is an area where there is no probability of finding the electron. Okay, so this node means that at some distance from the nucleus, there will be no probability, no intensity, if you want, of that electron wave in that region. Okay, and so we kind of even see that above when we do our point pixel based calculations. There is this little area where there are no pixels, and that's indicating a node. A concept to use to justify this is when two waves meet, where one crest meets with a well in a wave curve, like a sine curve or a cosine curve, constructive interference, or better yet, destructive interference would occur, where we have the crest canceling a well, and we have no wave at a certain point. So that is the justification for no intensity here, recalling that electrons can behave as waves. Destructive interference, eliminating the likelihood of finding an electron at that spot when n is greater than 2, or greater than 1, greater than 1. Okay, moving over to the next s orbital. So we're going to use an L equals 0 here again. We're at a higher n value this time, n of 3, and we can have a combination with n of 3 and L of 0, and so we do predict that a 3s orbital should be possible. And we're going to see similar ideas. We have the pixel-based representation of probability of finding the electron above. We're higher in energy level, n equals 3, and we're going to expect to see now 2 nodes where there's no electron probability, owing to the fact that we're in n equals 3, and we've got some destructive interference for this three-dimensional wave that is our electron. Okay. Clearly, you can see from the graph, the probability of finding the electron is allowed to kind of be located at further distances now. So when we cut this off, we end up with a larger volume allowed for the 3s orbital, and we've got our 2 nodes of no electron probability within that. And this is our 3s orbital. So we weren't able to put it on this slide, but 4s orbitals are known, 5s orbitals are known, 6s orbitals are known. So ideas like how the energy level of the s orbital series continues to increase as we increase n is correct, and how the size of the s orbitals tracks with the n value is also a correct idea. So as we go to higher n value for the ns orbital in question, we expect the size to be correlated to that n value. and also the position of that orbital on an energy scale, as we'll see later in this video. Okay, so those are just the s orbitals. We know that p orbitals are allowed, so p orbitals occur when we start to see L equal to 1. Okay, so we can see them show up only in an n of 2 and greater. So we'll start to see p orbitals show up in an n2 of greater. And as we saw in a previous video, because the m sub L options, we will now have 3 of them. So in this case, we can have a -1, a 0, and a +1. We expect to be able to orient these p orbitals in 3 different ways. And so down below, we have that reflected, where we can orient this figure 8 type orbital, or a dumbbell, if you will, along the x-axis, along the y-axis, or along the z-dimension. And this allows us to permutate and apply the 3 m sub L angular momentum quantum number options. Okay, ideas like we have in the probability map and nodes are still applied here in a p orbital. They're a little bit more complex to show because we have now differences along each axis. So you'd have to have in these two-dimensional graphs, a y versus x, to specify all the details of something this complex in shape, we'd have to have several different graphs to show the same the total information there. Okay. D orbitals arise when we have L options allowed at 2. And so the m sub L options there would be -2, -1, 0, 1, and 2. So 5 options there. So we saw that we can get 5 d orbitals. Out of that case, 1 is shown here. We're unable to show the other 4 on screen, but 3 of the other 4 also look like this kind of clover leaf, just oriented different. And the m sub L options help us rationalize that. One of them looks like a donut with a dumbbell kind of reaching in the middle of the donut. So we'll see that on the follow-up slide here. Okay, so that is how we kind of think of electrons as wave, and now we have orbitals for them. And we now need some tools to be able to predict the order in which they would be located on an energy scale. Okay, so we've shown this before, where we had an energy scale shown here. What we want to use is the periodic table to help us predict the order of these orbitals, as you see here. So the lowest one on this graph is the 1s, the next is the 2s, the next thereafter are the 2p's, thereafter the 3s, etc. And it looks like a bit of a random assortment of those options, but if we look carefully at the periodic table and note a couple things, we can use the periodic table to predict this order. So your periodic table from your textbook is here. A version that speaks to some additional information that we need to memorize is shown here. We need to know that the first 2 columns are what we call the S block. So this is the S block shaded in blue. Okay. If we jump sort of in order, if we're walking in order of elements, going up by the number of protons in the nucleus, the next kind of territory we come to is those shaded in red. And everything kind of shaded in red here, or pink, is what we call the P block. Okay. So that's the P block area of the periodic table. Notice that things like the boundary between nonmetals and metals are not shown here. So even elements below the staircase boundary are p block elements. And 2 other areas that we note here are the D block, the area for the transition metals. And so that's that skinnier part of the periodic table. And then the area that is shown sort of outside of all of that is the F block. And that's where we see lanthanides and actinides. Okay, so knowing that the blue area is the S block and the pink area is the P block, and the sort of peach area is the D block, we can start to predict the order of the orbitals that we see here on this energy scale. So let's and learn by doing. Let's look at arsenic, trying to predict all the orbitals that would be needed to describe the arsenic atom. Okay, so what we do is we start at hydrogen and we walk our way all the way to arsenic, respecting now the labels for the area that we are in. Okay, so the first spot is, of course, hydrogen, and that would be a 1s option. It's the first option, an N of 1, and it's our first element in the S block, so that's a 1s. Now when we jump across to the next spot, that's where helium is, we have a bit of an exception there. We're going to call that 1s2. 1s2. Okay, so there's our first option. We know that we can use each orbital to house two different electrons because I can put an m sub s equal to a half positive or negative a half positive, and so that is how we rationalize that. So there's our first option there. Our next option would be going down to the next row. So we're now here at n equals 2, second period of the periodic table. And so we're going to be 1s2 for the hydrogen, and now we're 2s1 for the first element, 2s2 for the second element, and we've just satisfied there. So we cannot create 2s3, there's no more elements thereafter. 2s4, there are no elements thereafter, so those options do not exist. Okay, we now have to jump across to the P block, and so here's where we start to use the P terminology. Okay, so now we're getting into a good pattern. And we're still in the second row, so we're going to use 2P for the next set. So again, walking across, we started 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. 6 electrons are allowed in the 2p option. And again, ideas about what fourth quantum number are allowed tell us that we should only have 3 options there. The 2p set with room for 6 electrons, given that we can use a half and minus a half in each of these spots. Okay, the next would be now into the third row, the third period. So now we have to go to 3s. So the next predicted orbital would be the 3s1, 3s2. We would see those right there. That's the next order in our periodic table. Thereafter, we take a jump. We go over to the P block. So we've already used 2 P's from below, so now we have to use 3 P's. And again, 3P1, 3P2, 3P3, 3P4, 3P5, 3P6. We're at the argon element at this point. So we've just made room for 6 electrons, where 2 could be located on each of those dashes to represent an orbital. One could be a spin value of a half, the other could be a spin value of minus a half. Okay, we're still not at arsenic. We have some more territory to cover. And so we'll go to the fourth row, the fourth period. We now have to use a 4s. So we're going to do 4s1, 4s2. That's the next one in our order. And we're out of S block elements there. Okay, we then are now into the D block, getting us closer to the arsenic over here in the middle of the P block. So a trick here is, even though we're in the fourth row, we start with 3D. Okay, so notice that. That's something to remember there. We start with 3D. That first option in the D block, 3D1. 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. There are 10 elements, and then we end the D block. 10 divided by 2 for the two M sub S options gives us 5 little dashes, all at the same energy level. Lastly, we can move over 3 spots to finally get to arsenic, and we can see here that that would be now reflecting 4. So we go back to the principal quantum number 4, and we have the 4p options, so 4p1, 4p2, 4p3, and finishing off the row, 4p4, 4p5, 4p6. Okay, 6 divided by 2 would be reflecting 3 options for those 2 electrons. Okay, and so forth. So you can keep going even past arsenic here and show that the next one is 5s1 and 2, and then thereafter we would be into the 4ds. Notice that the principal quantum number is 1 less than the row when we're dealing with D block territory. 41, 42, 43, 44, 45, 46, 47, 48, 49, 4d10. And then we would be into the P block again, and you can see here we would expect the next area to be 5p, so 5p. Okay, and we would expect 3 dashes there, 1, 2, and 3, given that there are 6 spots in that P block there. Okay, so that's how we use the periodic table to predict the order of the orbitals for understanding where electrons could be located. Okay, so with that, we're ready to cover a couple of rules now. We know how to predict the order. That is, we know how to reproduce the dashes on this graph in order using the periodic table. Next, what we need to do is consider using the options, the dashes here, per the number of electrons that we are allowed in an atom in question. Okay, so the Aufbau principle is going to help us here. So the Aufbau principle tells us that for ground state atoms, where they're allowed to be at the lowest energy situation, so we haven't injected a photon, we haven't excited the atom, what we do is we consider filling electrons into the lowest energy levels first. Some people think of pouring water into a cup. The water will locate at the bottom of the cup first and then fill its way up as you pour in more electrons into this quantum mechanical cup that is our atom with all these spots for electrons. Okay. To help us, we also have Hunds' rule. And Hunds' rule says that the maximum number of unpaired electrons, that we should be maximizing the number of unpaired electrons within an orbital option. Okay, so we'll see that through an example here as we build up a couple of electrons. But if we, in short, if we can unpair electrons, we want to. Okay, so imagine a situation where we are putting electrons in the 2p options. We would want to position those electrons apart first and then pair up electrons after. Okay, so that's the idea there. So Hunds' rule is maximize number of unpaired electrons in a set of orbitals at the same energy. Okay, a set of orbitals at the same energy. There's one set right there. We would want to unpair the electrons first, and then if we have to apply extra electrons, then we would start to pair them up. Okay. Good. So let's remind ourselves how to do arsenic here quickly. So we saw that the arsenic element, we can see here, is the 33rd element. So we expect 33 electrons to be needed in the neutral atom that is arsenic. And so we have to consider pouring 33 electrons into our energy level diagram that we can predict. So repeating the exercise of walking from the periodic table all the way to arsenic, this is something you should try. Okay, so if you want to pause the video at this moment, see if you can predict the order in which we should get there. So you might try that on this slide here without looking at the P block and just your periodic table. So in other words, don't look at our energy level diagram here, but just use your periodic table and see if you can reproduce the order here. Okay, if you resume the video, you should get something like the following. So we predict for arsenic, AS, that the order should be 1s, and we can position up to 2 electrons here. Then 2s, so we've just gone from hydrogen, helium, that's the 1s options. 2s1, 2s2, okay, so we could have a 2 there. We're now walking all the way across here, so we're into the P area now, so we can have a 2p, and we could put a number as large as 6 there. N of 3 this time, so 3s, and there are 2 options there, so I could put a number of 2 there. I'm now into the next 6 elements over in the P block, and so those are the 3 P's, and I could put a number as large as 6 there. And then when I move to the next area, I'm into the 4th principal quantum number, or the principal quantum number of 4, so 4s, and I could put a number as large as 2 there. I'm now into my D block for the first time. So here's the exception. I have to use a 3 at this point. 3D, a number as large as 10 there, would take me all the way to the zinc atom. And now I'm into the final P's needed to get me ultimately to arsenic. So we go back to 4, and I've got a 4p, and I can put an option there to take me to that arsenic. So we said 33 electrons, and so we can start to use our options. We know the 1s orbital can have 2 electrons. We typically indicate the m sub s of a half. We can use a half arrow. And then an option that's negative 1/2, we can use an upside down half arrow. Okay, so I'm going to show those here. Forward half, an upward pointing half arrow, a downward pointing half arrow. There's 2 electrons, and I'm going to put a 2 there on my electron configuration to indicate that. 2 of the 33 electrons have just been assigned in this ground state arsenic atom. Okay, 2 more electrons. 1, 2 in the 2s. The 2p, I have room for 6, so let's go ahead and use 6. 1, 2, 3, 4, 5, 6. Notice that we ended up fully paired there. To better show the filling exercise respecting Hunds rule, I'll redo that as if we were pouring them in one at a time. So we would first unpair the electrons, maximizing the number of unpaired electrons in a set of orbitals at the same energy level. Then I would pair up my last one. So the 4th electron, the 5th electron, the 6th electron. Okay, so there's 6 in the 2p. I'm going to put a 6 down there to keep track. The 3s is next. So remember, we're here walking all the way from sodium to magnesium. So 1, 2, 2 electrons there. 3p, so we'll do it here respecting Hund's rule. 1, 2, 3, 4, 5, 6. I've just used 6 additional electrons. What's our total? We can take a little bit of inventory. 10 electrons here. I've now done 8, so 18 electrons. I'm at the 18th element essentially here, so I'm all the way over at argon at this point. Let's keep going. The 4s can accommodate 2 electrons. 1, 2. The 3d can accommodate another 10 now. So you can see the next area up the energy level diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. And now we can do the 4p's. 1, 2, 3, 4, 5, 6. 4p6 would take us all the way over to krypton. We can take stock of our electrons. We had 18 plus another 18, that's 36. That's too many electrons. We only wanted 33, so let's back off 3 electrons. Which 3 electrons should we remove? The paired ones. So we'll remove those and adjust our 4p value to reflect actually the total of 33. Okay, so we'll go 1, 2, and 3, and adjust our count down below as well. Not 4p6, but actually 4p3. Okay, there's the electron configuration in order, showing the energy increasing as we go up. So this is increasing energy written out in a script showing where the electrons are, with the superscripts on the orbital in question reflecting the rough energy level on the energy axis and showing some shape information, S and P, and the superscript numbers indicating the population of electrons in that energy category, in that orbital category. Okay, so to clean that up and show you a little more quickly so we can break away from this video, the arsenic is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and finally 4p3. Okay, ground state electron configuration. An excited state, sometimes indicated with a star, where a photon has promoted an electron out of an orbital. Might be a photon could be used to promote an electron out of here and put it at a higher energy state. Okay, so a photon has to be absorbed. Energy would be absorbed, and we can put that up there. So an excited state argon, to show the difference there, is going to look different, and it's going to break Aufbau's rule because we've put in energy to break it, and so we'll do that. So in this case, everything you see there is the same up until those last levels, 3d10, p2 this time, and we're now showing that a 4d has a single electron. So this last one, make careful note here, this is an excited state electron configuration where something has been used to break the Aufbau principle, and that indicates that a photon has been absorbed to break the Aufbau principle and give us an electron at a higher energy level and leave a lower energy level empty. This option, we could have promoted any electron below to a higher energy level. We would just need an appropriate photon of that energy to help us do that. Okay, we'll continue on some of these ideas in the next video.